Good morning, Mr. Ganye. I'm here to present Physics IGCSE 0625, crossing the core and the extended options. Our topic for today now is energy. We have selected some objectives from the IGC Physics syllabus, topic energy, where we are required to identify the different types or forms or states of energy. You can use all those words as g.p.e, gravitational potential energy, chemical, elastic or strain energy, nuclear energy, kinetic, mechanical, sound, light, thermal or heat, and internal energy. You are also required to describe energy transfers during events and processes. This is energy changes. We are required to apply the principle of conservation of energy. We are also required to do some calculations on energy, where we are required to use the expression that kinetic energy Ke equals half mv squared, and change in gravitational potential energy equals mgh with a change in height. Then at the end, we are supposed to describe how electricity and other useful forms of energy may be obtained from different energy sources. Production of electricity from different energy sources. We are also going to look at efficiency, where we are doing some calculations on efficiency. We move on. As usual, our lessons, we are starting with a task that you need to do before you move on to the lesson, just to show that you are ready for the lesson. Our task here is to list the different types of energy. From your background knowledge, you need to list the different types of energy. Describe the different types of energy. Here we are looking at these types of energy. Then give the sources of these different types of energy that you've done. So it's a pre-task that you need to do as you move into your lesson on energy. We move on. Having looked at that, we are now looking at the types of energy and describing them and giving examples as shown in this table here. We've got energy type, kinetic energy, which is energy due to motion or movement. For example, any moving object, we say it possesses kinetic energy. Any moving object possesses kinetic energy. We have gravitational potential energy, which is g.p.e. In most of the questions or papers, it will come as g.p.e. g.p.e. This is energy from the potential to fall, energy of position, where we are saying any object which is not resting on the ground or on earth already has the potential to fall. It already has g.p.e. because of its height. For example, here, a book on a shelf, because it is a certain distance or a certain height above the ground, the earth, that book already has potential energy, in this case g.p.e, it can fall. So g.p.e is energy of position due to height. We have chemical potential energy, which is energy stored in chemical bonds, in chemical substances, mostly fuels, and the food that we eat, we get chemical energy. Example here, we have glucose molecules have energy, starch has more bonds, has stores of more energy. So we are saying all these food molecules that we consume, they have chemical potential energy. We also find this one in other substances, other chemical substances. Then we have strain or elastic potential energy. strain or elastic potential energy, which is energy we are finding in something which is compressed or straight. You are looking at your elastic bands, your springs, they have this energy, elastic or strain energy. We have nuclear potential energy, energy released when particles in atoms are rearranged. This will come in again as our last topic in physics under radioactivity. If you remember very well, you will look at nuclear reactions there, radioactivity. We are saying we've got radioactive substances which, when they collide with neutrons, they give us this nuclear energy which we can use. So this is energy released when atoms are made to decay, radioactive decay in a nuclear power station, and we get a whole lot of energy from that. Internal energy is a combination here of kinetic energy and potential energy. We have a combination of Ke, kinetic energy, and potential energy. This one, we usually get it when an object falls to the ground. On hitting the ground, there we have internal energy there. And also when objects are heated, temperature is increasing, their internal energy also increases. We have electrical potential energy, energy carried by electrons. This is electricity, energy that we get from sources like batteries or these other energy sources. Then we have got light, sound coming in there. So these are the different types of energy sources that we have, which you should have looked at in your task. We move on to energy transformations and energy conversions. We are saying energy can be transformed from one form to another, from one type to another. For example, here we have a rock falling from a cliff. Is a rock which was on top there on a cliff, and the rock is falling. Because it was on top of the cliff, it had g.p.e, gravitational potential energy. And now it's falling, that is movement coming or falling downwards, it has now Ke. And we are seeing that g.p.e, which it had here, has been transformed to Ke, kinetic energy. So when we move, our cells turn chemical energy. When we are doing our daily activities, we have chemical energy inside our bodies from the food that we've eaten, which is now converted to thermal energy, which someone can call heat energy, and also kinetic energy, the movement that you are doing with your muscles. We introduced the principle of conservation of energy. Principle of conservation of energy, which states that the total energy in a system remains constant, and energy cannot be created or destroyed. It can only be converted from one form to another without any loss in total energy. So that is the principle of conservation of energy. You need to remember this and put it down in your exams. Conservation of energy. We are saying energy cannot be created or destroyed. It's already there in a certain form. What you can only do to that energy is to transfer it, to convert it into another form. Then you can notice it. For example, simple example going back is this rock falling from a cliff. Because it was on top of the cliff, certain height above the earth, it already had g.p.e. It had potential energy, gravitational potential energy. Then it was falling Ke. So we didn't create the energy there. It was already there, but in the form of g.p.e. And is now being converted or changed to Ke, as shown there. So energy of a system remains constant. It's not increasing or decreasing. We are only converting from one form to another. We have another example here illustrated on this electric bulb or light bulb, which is receiving electrical energy, 100 joules of electrical energy coming in. We know it's an energy converter. It's going to change some of this energy to heat, some of this energy converted to light. So we are saying we are not creating these. They are already there. The energy is already there. Electrical energy, in this case 100 joules. Then it is converted or transformed into heat energy and light energy. Now, if we add the total energy here, after, in the system here, at the end here, we are saying 98 plus 2 joules, it gives us 100. So we didn't create energy, we didn't destroy energy. It's that the energy is existing in different forms. The other side, heat energy, the other side, light energy. So in any energy conversion, the total amount of energy before and after the conversion is constant. The total amount of energy before and after the conversion is constant. That's what we are seeing there with 100. At the end we also have 100. But this second 100 after is appearing in different forms. Some of it is heat, some of it is light. We move on. Energy calculations, where you are now going to be able to calculate g.p.e, calculate k.e. We have our calculations here. The first one for g.p.e, gravitational potential energy. The g.p.e of an object of mass m at a height h above the surface or above the earth is given by the formula g.p.e equals mgh. g.p.e equals mgh. Your mass for m multiplying your g, gravitational field strength, and your height. What are the key things under this formula? We need our mass, and this mass should come in kilograms, standard units of mass, kgs. Our g is the gravitational field strength, and on earth here we are using 10 newtons. It is actually 9 point something, but for simplicity we use 10 newtons for our calculations. Ig we use 10 here. Then your height of the object above ground, and this height is in meters. You have to do the conversion to meters. They can give you this height in centimeters. Do the conversion to meters. Those are the key things to take note, especially in the extended option or extended paper. Same thing with your mass. It has to be in kilograms. They can give you this mass in grams, and you have to convert it to kilograms. We move on. Our second calculation is KE, kinetic energy of a moving object of mass m with a velocity v, is given by this formula here. KE, kinetic energy, equals to half mv squared. Half multiplying the mass in kilograms, multiplying the velocity squared, or the speed of the object squared. Don't forget to raise it to the power of 2 to square. And again, tip there, your mass should be in kilograms. Then you multiply it into your formula. The derivation of these formulas is not part of our syllabus. You should not worry about that. So we have our calculations there, which are going to use later on in some questions. g.p.e mgh. KE half mv squared. We move on. We are now using those formulas to calculate KE, and the other one will be calculating GPE. Let's look at this one. Calculating KE, kinetic energy. Kinetic energy equals to the half multiplied by the mass multiplied by the speed squared. Don't forget the speed squared there, which is KE equals to half mv squared, shown here, half mv squared. Your mass is in kgs, your v, your speed, your velocity in meters per second. Then your kinetic energy should come with the units of joules, capital letter J. Capital letter J. The units of energy there are joules, capital letter J. For example here, a football of mass 0.4 kgs, which is 400 grams, moving with a velocity of 20 meters per second, is a ke of, let's do the calculation there, ke equals half mv squared. That's our formula there. Always remember to write your formulas. They are credit marks or method marks which are always given for formulas. You substitute now, you check that all your units are in standard units, like your mass is appearing in kgs, which is okay, is correct, and your speed there. So half multiplying your mass 0.4 multiplying your speed or your velocity, which is 20. You compute that in your calculator, you are getting the final answer as 80 joules. Usually when you are doing your calculation, don't worry about putting units here. You can just use the numbers, don't worry about the units. Just put the unit on the final calculation here, 80 joules. So we are going to have another task here which you are going to do. As you move along the lesson, you are required to calculate the ke of the following. A 1 kg trolley traveling at 2 meters per second. If you follow it, you can see that you are given the mass and you are also given its speed or velocity there. A 2 gram bullet traveling at 400 meters per second. A bullet which has been fired is of 2 gram. Then you are given the speed. You can use a simple calculation for ke. Of interest here is that the bullet, they gave us the mass in grams and they've also converted it to kgs, which means this is a very important point when you do your calculations, especially extended calculations. Take note of units. Well, they can give you the mass in grams. You have to do the conversion to kilograms. We move on. We have a calculation for g.p.e. Calculation for g.p.e. Calculating gravitational potential energy. Gravitational potential energy equals to the weight times the height of the object above ground. Where is the weight coming from? Let's go to the next formula. g.p.e equals mg. If you follow your notes, your syllabus, we know that mg is the formula that we use to calculate weight. So that is the relationship there between g.p.e and bringing in weight in there. Because mg is your weight. Our formula, g.p.e equals mgh. When an object is falling or is raised above ground, it is doing work. That's why we are now marrying in another formula there and say work done by a force. Because weight is a force which is moving a certain distance, linking with another part which we are going to look at later on, work done or work. You are going to see that at the end of the day we are saying g.p.e is the same thing in calculation as your work done. And we use the same formula here, force multiplied by vertical height. Force, in this case, your mg, which is your weight also, multiplying your h, which is your height. And you get your potential energy is mgh. Let's have an example here. When m is the mass in kilograms, g, your gravitational field strength, which we said we are using 10 newtons per kg, 10 newtons per kg, or your acceleration due to gravity again, which is 10 meters per second squared, and your height in meters. Look at that, standard units, your height in meters. If the height is given in centimeters, you have to convert it to meters. So the potential energy is going to be recorded in the units of joules. Remember, the units of energy, the units of work done are the same, joules. So, for example, the potential energy gained by a 0.1 kg mass raised vertically by 1 meter. Substitute into our formula, mgh, your mass 0.1, multiplying the gravitational field strength, which is 10, multiplying your height, which is 1 meter, we get your g.p.e possessed by this object is 1 joule there. You can compute that in your calculator. Then you've got your task that you are moving on to do there, based on what you have said, mgh, or calculating gravitational potential energy. Calculate the potential energy of a 5 kg mass, shown here, when it is 3 meters and 6 meters above the ground. 3 meters and 6 meters, that is your height. So we are doing two calculations, part 1, part 2. Your G value here is given as 10 newtons per kg. So we are going to use that. Then we've got another one, a 100-gram steel ball falls from a height of 1.8. Then you are supposed to calculate the g.p.e. there. What is of interest in this question is the mass recorded in grams. Please take note there. There's a conversion which you have to do. We move on. We are now using the principle of conservation of energy in a calculation. Remember, we talked about it. If we can go back a bit to the principle of conservation of energy, where we are on this slide, where we said the energy of a system remains constant, energy cannot be created or destroyed, it can only be converted or transformed from one form to another. Where do we use this now? We are going to use this on some calculations which we have, where you are marrying your KE and your GPE. And interestingly, they are going to be using either the formula for GPE, which is mgh, to calculate KE, and the other way around, using the formulas for KE to calculate GPE. Both they are saying these things are the same, energy is being conserved. Let's follow this example here. When a mass m at a height h above the ground is potential energy mgh, with our mass m here shown on the diagram here, it is a certain height above the ground h, because it is not resting on the mother earth. We are saying it has got GPE, which is mgh. It's not moving, so its KE is 0. And we are saying at this level, the system has got only GPE, which is mgh. Then, point number 2, when it falls, this mass of ours here is going to fall. Its velocity, speed, increases and it gains kinetic energy. Because it's falling, it's moving downwards, it gains KE. And at the expense of potential energy, it's losing GPE because it's losing height. Some of that GPE is being converted to KE. This is what we have here now, in motion here. And we are saying, as it is moving like that, somewhere in the middle here of its motion, the GPE plus the KE, it has GPE and KE. Because it's above ground, it has GPE. Because it's moving, it has KE. A combination there. So energy already has been transferred or converted from mgh, which is GPE, to KE and GPE, a combination there. Our object continues to fall to the ground here. On hitting the ground, on resting on the ground here, it no longer has GPE. The GPE is indicated 0 here. It no longer has GPE. It only has KE, kinetic energy. And we are saying that KE now, its value is equal to the GP which it had up here. So we are seeing that according to the principle of conservation of energy, the loss in GPE which was happening was appearing again as a gain in the KE of the object. So loss of GPE equals gain of KE. We are applying the principle of conservation of energy here. We are saying energy is not lost. Energy is being converted from one form to another. Let's look at this again. You will be required now to do calculations based on this idea that energy is conserved. Where on hitting the ground here, you are required to find the speed or the velocity of the object, the mass on hitting the ground. And you see that you don't have the KE, because the formula which has got speed is this one for KE. So for you to do that calculation, we are saying instead of using half mv squared as your formula, you are now going to use mgh, the formula for gravitational potential energy. And they will ask you there in the question, what assumption did you make in answering this question? And the assumption that we've made here is that the principle of conservation of energy is in work. Energy is being conserved in this system. Loss in g.p.e equals gain in k.e. So you can use the formula for k.e when you are calculating mgh. At the same time, you can use the formula for mgh when you are calculating or doing calculations which have to do with ke, because of the principle of conservation of energy. We move on. We still have the same thing here. For a free falling object of mass m, its gravitational potential energy is converted into kinetic energy. Take the ground as the reference level. So at the ground, right on the earth, our g.p.e is 0. There is no height, so g.p.e is 0. So we have the same diagram as in the previous slide. The object is falling. It was at a certain height, and g.p.e there was mgh, there was no ke, it was not moving. It's now falling, moving downwards. On hitting the ground, or just before hitting the ground, or on hitting the ground, if there is no more g.p.e there, all its energy is appearing in the form of ke, kinetic energy. So we are saying if it had 100 joules up here of g.p.e, it means at the bottom here its ke is also 100 joules. They are equal. Loss in g.p.e is equal to the energy gained in ke. We have the same calculation. We are applying the principle of conservation of energy, assuming that there is no air resistance. We are saying the total energy at height h, which is the g.p.e, equals the total energy at the ground, which is half mv squared. So our formulas are the same there. mgh is equal to half mv squared as shown here. mgh equals to half mv squared as shown here. So you can calculate either or any of these using the other formula which is given there. Note the total energy of object is constant. It didn't change throughout its fall. Not just at the two positions, but throughout its falling. The total energy did not change. It was constant, but it was appearing now in different forms. At one stage it was g.p.e, the other stage ke. Especially halfway here on the diagram here, we have both g.p.e and ke as shown on the slide here. I'm going back here where we have g.p.e and ke together here. And if we add this, the equal will always be, the total here is always 100 joules if it is an example of 100. Let's say we started with 100, it means here we also have 100 but in different forms. Maybe 50 g.p.e, 50 ke. Then here we all have now full ke, which is 100, and g.p.e 0. So we can apply the principle of conservation of energy in calculations. Let's move on. We have got a task which you are going to do as you revise your materials, where you are supposed to apply the principle of conservation of energy on a calculation. You are going to do your calculations there. Question 1, 100 grams steel ball falls from a height of 1.8 meters onto a metal plate. It rebounds to a height of 1.25 meters. Find A, B, C, D as shown there. A, the g.p.e of the ball before the fall. It means the height is 1.8. Take note of the mass. Like I've said before in this question, take note of the mass. As a tip there, look at your mass. There's a conversion which you have to do. Then you continue to do the calculation. There's another one here. A boulder, a rock of mass 4 kg rolls over a cliff and reaches the beach below with a velocity of this 20 meters per second. Find A, the kinetic energy of the boulder as it lands. Ke of the boulder as it lands. So you do the calculation there for Ke. The potential energy of the boulder when it was at the top of the cliff. There is some way you have to apply the principle of conservation of energy. We move on. There's another example there. A ball drops a ball of mass 0.5 kgs. The ball falls a distance of 1.1 meters as shown in the diagram, ignoring air resistance throughout this question. So 1.1 there, distance or height, and the mass of the ball given here is 0.5. Then you have your calculations that you are supposed to do there. Calculate the decrease in g.p.e, gravitational potential energy, as it falls. So calculate the g.p.e decrease. Then B1, the ball bounces and only rises to a height of 0.8. It rebounces 0.8. Look at that height. Calculate the energy lost during the bounce. Do your calculation there using mgh. Then look at the last question now. On another occasion, the boy throws the ball down from a height of 1.1 meters, giving it an initial kinetic energy of 9.0. Calculate the speed of the ball as it hits the ground. You are required to calculate your speed, your v, which is on this formula here. So we are applying principle of conservation of energy. Energy sources. We move on to energy sources. Remember, our topic is energy, and you are required to look at energy sources, the different sources of energy that we have, that we use. We need to identify renewable energy sources, those that are inexhaustible, that we can have for a long period of time, can replace them in normal time. Then we have got non-renewable energy sources which are exhaustible. Once they are used off and they are finished, that's it. They take a whole lot of years to have them and won't be around. They cannot be replaced in time. Those are NR, non-renewable resources. So you need to classify your energy sources into these two as you do your revisions. Classify which ones are renewable, which ones are non-renewable. We've got all these energy sources listed here. Biomass, gas that we use there, coal, hydroelectric, nuclear, and other renewables there. Then oil, main one, oil, where we get most of our petrol, our diesel, and the like. When picking an energy source to use, you look at some costs that you have to incur in setting up the plant and in using it everyday expenses. So when you compare your energy sources and the advantages and disadvantages, you need to highlight or to bring out issues like costs. The cost there, is it on starting to build the project or on running it? You need to separate the two as you answer your papers there. Reliability, is it always available? Some of them are seasonal. They depend with the weather, with the climate. So you need to mention that in your advantages and your disadvantages. The scale. Here we are looking at the supply. Is it large enough, or do we get a small supply? Can we supply a large community, or it's for individual use? You need to look at those. Then lastly, you cannot do away with the environment. You have to look at their environmental impact or damage in using some of these sources. Some are not good for the environment, some are good for the environment. So you need to look at that as part of your discussion on the advantages and disadvantages of these energy sources. So you need time to look at that. Classify each and every energy resource as either renewable or non-renewable. Go on to discuss its advantages and disadvantages with these headlines in mind: cost, reliability, scale, and environmental impact or environmental damage. And you need to give more details or information. Don't generalize. Right, we move on. We've got a summary of those energy sources, their advantages, their disadvantages, and how they release they work. In this case, we are looking at how do they release electricity. How do we get electricity from these energy sources? We have this group that we've bunched together here: oil, natural gas, and coal, which are chemical energy sources here. They are starting with chemical energy. They store chemical potential energy. Oil, yes, that is chemical energy there. Natural gas, which is mostly methane, it's also chemical. Then coal, carbon, is mostly, again, it's chemical there. Then we are using it. How do we use it? We have to heat it, burn the fuel. So we have chemical to heat, following the energy conversion there, chemical to heat. Then the heat that we get there is used to boil water, which will be in large boilers there. And from that water, we get steam. We get steam, which is now coming out of the boilers at high pressure, directed towards some turbines. And those turbines rotate. They are forced to rotate because of the steam which is blowing on them at high pressure. So we have started with with chemical energy. We went to heat energy. We are now on kinetic energy. You are following the energy conversion. You need to extract the energy conversion from there, chemical to heat to KE. As the turbines are turning, they also turn the generators. Turbines are not generators. They are working end to end with generators. So we have chemical to heat to KE, then electrical as the energy conversion for this one. Most of these, they have the same setup. Burn them, produce heat, kinetic, then electrical. What are some of the advantages? Disadvantages, they are shown there. You can run through them. Advantages, they are easy to combust, easy to burn. It's fairly cheap when you use it. It's reliable, always there. It's not affected by weather or climate changes like others. You can do that in a comparing with solar, comparing with wind and the like. Then the disadvantages, they are polluting to the environment. Harmful byproducts are released into the environment. During the mining or extraction of these, there is damage to the environment, there is displacement to the natural habitat of animals. All those things, you comment on them under the disadvantages. Pollution, air pollution is also there. So that is the first group of energy sources. We move on. The second group, we have tidal, hydroelectric, geothermal, nuclear fission, and solar. And if you look there, most of them are renewable. Tidal, hydro, geothermal, all these are renewable sources which we have. But nuclear is appearing there, non-renewable. How is the energy removed? In this case, we are saying how do they end up producing electricity? All these energy sources, we are looking at them in line that they are producing electricity at the end. Tidal, hydro, they nearly have the same concept. You are trapping water in a reservoir which is elevated or above ground. So because they are above ground, they have g.p.e, gravitational potential energy, and the water is allowed to flow down. That is ke, movement of the water. Again, movement of the turbines because of the water which is splashing on them, and that generates that causes the generators to also rotate. and to convert KE to electrical energy. So the energy conversion there is g.p.e, because of the height above ground as it is trapped in a reservoir or a dam, to KE. The KE is for the water moving and the turbines moving, and electrical for the generator. So we have that. Look at the advantages and disadvantages there. Tidal, there are no byproducts which are damaging to the environment. Is there, always there. It's expensive to set up this one now. It's expensive to set up. Then there's also disruption to the natural habitats or environment of other aquatic animals. Look at hydro, same thing. Under disadvantages, there's displacement of humans. Because for you to set up this reservoir or this dam, you need a large area to be cleared, so you are disturbing the natural environment. It's a disadvantage there. Then it's very costly to start it up. High initial capital. Remember we talked about costs the other time. Very expensive to set up this one. Advantages, non-polluting products. Over time it's easy or cheap to run, to use it every day. It's cheap. Reliable, it's always there. The moment you have your water trapped in there, you can as well have a supply of electricity. We have geothermal, where water is pumped into underground or into the ground, and that water is heated by natural heating systems there of the rocks which are under there. So heat energy is used, and this heat energy is coming from the rocks underground. We produce steam at a high pressure. The steam which is coming out at a high pressure is directed towards some turbines, and the turbines rotate. That's kinetic energy. At the same time, the generators work, produce electrical energy. So it's a renewable, it's natural, this one. Very reliable, always there. No harmful products to the environment, but they are high initial capital costs when you want to start it up. Then it's limited, that is only available in certain areas. Some areas they don't even have these hot springs which you can make use of. So it's limited in locality. We have nuclear reactions, nuclear fission. We are using nuclear energy there, which is stored in chemicals like uranium-235, uranium-235 shown here as the isotope. And you bombard this uranium with neutrons, and a reaction takes place where it releases a lot of heat energy. Then the heat energy is used to boil water again, producing steam. Then the steam turns on your turbines, then your generator like that. So this one should be near a good supply of water, a sea, like that. It releases quite a large amount of energy, and most of the countries are moving towards this one, although with a lot of environmental concern is a disadvantage there. A large amount of energy, very reliable once you're able to do it. No pollution in terms of greenhouse gases, but it comes with this lot of disadvantages which are here. It's expensive to build or start up, and also to maintain. Expensive to decommission it at the end when you no longer want to use it. It's not easy to dispose of nuclear wastes. Remember, we'll look at this again under radioactivity as a topic at the end of the syllabus. Then it produces a lot of radioactive waste which are difficult to manage or to decommission. Then we have solar, renewable, and making use of the sun, and use solar panels, solar power plants. So we have all these energy sources. You are looking at them in line with producing electricity. We are looking at these energy sources in line with producing electricity. Thank you very much. That was our lesson on energy.